All right, so
That's it.
the last talk of this session and the meeting will be given by Yasir Iqbal from IISc, and he's going to answer the question that do the square, Shastry-Sutherland, and the checkerboard lattice share the same spin liquid.
Great. Thanks to Didi and thanks to all the other organizers for thinking of me to have me here. Really enjoyed and still doing so. So this is a evolving story. Part of it is published, part of it is still data is coming in, even till 5 minutes before I was changing something. It's to do with, as Subir mentioned, there's a long saga of finding spin liquids, arguing about spin liquids in different models. And I think there are 3 celebrated models in search of spin liquids that have garnered much attention. In that talk, he was referring to the square lattice J1, J2 model. And there's also a Shastry-Sutherland lattice, which now, in the last few years, there's mounting evidence for a spin liquid. And there's also a checkerboard lattice. And they all seem to be connected to each other. If you view it as a form of bond depletion, you can go from one to the other. The main message of my talk is that the spin liquids in these 3 lattices seem not to be isolated cases, but rather the 3 lattices, and when you go from one to the other, they actually all share the same phase. They're in the same spin liquid state. So, So this is a schematic phase diagram I show. So you have the square lattice, which is denoted by these black bonds, and the Heisenberg antiferromagnetic interaction is called J1 here. You have some spin 1/2s residing on the vertices, and you can frustrate the Néel order there by introducing second neighbor interactions called J2, and at some ratio of J2 over J1 around 1/2. This is the long saga about what is the nature of the spin liquid. Now we understand what it is. It's essentially a D-wave spin liquid with massless Dirac fermions, but coupled with a Z2 gauge field, and ultimately descends from a parent pi flux state by coupling, charge 2 Higgs field to a compact U1 gauge field and then breaking the symmetries. So the second thing is, there is another lattice called the Shastry-Sutherland lattice, whose claim to fame is that it's one of the few models in 2 dimensions, few quantum antiferromagnets, which lend itself to an exact determination of the ground state, namely a dimer product state here. And if you view this, you can actually start adding the extra bonds and go from this to the other. So this can be viewed as a depleted version of this lattice. There is another lattice which has also garnered much attention, but and was much in fashion about a decade or 2 decades ago, called the checkerboard lattice, also called the planar pyrochlore. If you project a pyrochlore on 2D, it seems like this, where also you can go from this to the other by adding all the empty bonds, right? Now, it so happens that the evidence that I'm going to present to you is that all of these lattices share a spin liquid where you have Dirac fermions, which are coupled to a gapped Z2 gauge field, but the masslessness or the gaplessness of Dirac fermions remains intact. So that's what is called as a Z2 Dirac spin liquid, and it represents a stable phase of matter. That is, when you add fluctuations beyond mean field, it doesn't destabilize such a state, as opposed to U1 spin liquids, which are precarious, or SU2, which we know are unstable on bipartite lattice. Okay, so the story, So the phase diagram, just to recap, looks like this. It is taken from a paper from Subir, who developed a field theory for these transitions, that you have a Néel state, which is this cartoon picture is shown here. And when you frustrate with second neighbor interactions, you basically melt the Néel antiferromagnet and go into a tiny region of spin liquid behavior. The precise phase boundaries are debated within different numerical methods, but there is more or less consensus that there is a state which lacks any conventional dipolar order, and also lacks any translational symmetry breaking, which then ensues as you crank up the value of J2 before you enter into a columnar or stripe phase. A similar phase diagram has now come about on the Shastry-Sutherland lattice, where again you have a Néel antiferromagnet, which seems to melt and give way to a quantum spin liquid before entering into a plaquette and then this exact dimer product state. There were many old works. This work of Bernier, Kim, and Subir looked at also the possibility of a spin liquid in the checkerboard lattice, where using Schwinger bosons, they show that at small values of spin, there is a spin rotation invariant state, which they call the pi q short-range ordered state, because it arises as a quantum disordered version of an incommensurate spiral, the pi q. And this basically phase has above the gap deconfined spin-ons and is described by a Z2 gapped spin liquid. So the difference in perspective that I have that to sort of I'm going to claim is that we are working with fermions here, which of course have the versatility to capture both gapless and gapped phases, is that indeed it's a Z2 QSL, but it's most likely described by gapless Dirac fermions. So before I go into any proposing any wave functions for this, let's look at the evidence that maybe I go on the other side. It's the signal. Right. Yeah, okay, great. So the outline of my talk is going to be like this, that I'm going to present evidence from exact diagonalization on small clusters that there are three rivers of liquidity which eventually merge to form a triangle of spin liquidity connecting these three models. Then I'm going to come and start focusing on a particular spin liquid candidate for the Shastry-Sutherland lattice and argue that there is, let's say, some evidence from thermodynamics that it could potentially be realized in a recent material that has come into limelight. This is going to lead me to then try to pin down the nature of the quantum spin liquid by employing the formalism of projective symmetry groups. And here again, I'll try to make a case that there is only one spin liquid which actually can be continuously connected or connect these three kinds of lattices, which shares, where you can map these PSGs onto each other. Then I'm going to go beyond mean field and try to construct and include projected BCS wave functions and look at the effects of gauge fluctuations beyond mean field within a variational Monte Carlo approach, and then supplement it with other RG approaches, and then make the case that there is a universality and commonality between spin liquids on these three lattices, which is there. So, okay, great. So if you want to start from the square lattice, right? Sorry. There should be, yeah, okay. So you start from the Shastry-Sutherland lattice, which consists of only the squares and the red bonds. That is shown on this axis. So let's call this bond a J square, and this is the J dimer. So J dimer over J square, I already showed you the schematic phase diagram. This is here. Now, if you want to interpolate and go to the J1, J2 square lattice, you have to add all the missing pieces of the diagonals, which are shown in green here. And let's call them JD prime, whether they are the other one, this ones or through the empty ones. And that's shown on the vertical axis. When JD prime equals JD, that's the limit of the square lattice J1, J2 model, and that's the line that's shown here. Okay, so the first thing we did was to diagonalize clusters of about 20 spins and went up to even 32 spins and look and try to identify a window of spin liquid behavior by looking at the crossings of the gaps between the singlet and the triplet, which gives you the transition into the valence bond solid, and the singlet and the quintuplet, which gives you the transition into the Nail antiferromagnet. And this is how the phase diagrams have been obtained in literature from ED on many of these models, and show that there exists this river of liquidity between these two gap crossings where there is neither conventional dipolar Nail order, nor is there any translational symmetry breaking valence bond crystal order. And that this river of liquidity, this little window of liquidity that was here, actually continues all the way till the J1, J2 model and beyond. Heisenberg. Yeah, it's a three-component spins, all rotationally invariant, yes. So, right. So if you look at the gaps with respect to the ground state, they're more sensitive to finite size. But if you look at composite gaps between excited state, they're more robust to 1 over L. And if you do this, Anders Sandvik and company showed that this phase boundary remains essentially robust to increasing system size up to 40 odd spins they went. So we employed the same spectroscopic diagnosis and achieved at this phase diagram. And next slide, I'm going to show you even on 32 sites. So one thing is that there is not a tiny spin liquid, but an entire river of liquidity. That's the first claim. Yes. So it doesn't matter. It's, I think, quick bad plotting, as you will see. So this phase diagram has been obtained by ED, and behind you see another white hatch region. This is by IDMRG, and they're essentially overlapping and shown. Okay, so this is one aspect, that the spin liquid is not isolated, but there's another spectacular aspect. If you look at the level spectroscopy of the different excited states and different irreps, there is actually, starting from this point here, As you go up, that's the way to go here, there are no level crossings. So the low-lying levels essentially remain blind to the interpolating from this model to that model. And look at the gaps. They basically, there are no, till you reach the square lattice J1, J2, when all the mess starts coming up. That is well known. But entire way, there is nothing, telling you that there is no rearrangement of states much happening. The other evidence is, if you now take the wave function for the Shastry-Sutherland point here and compute its overlap with the rest of the phase diagram, with the exact ground state. You take the exact ground state here and compute the overlap with the exact ground state in the rest. Along this entire river of liquidity, the overlap remains more than 98%. And it's very large with the Néel state. So the overlap with the Néel state is around 98, 99%, telling you that this spin liquid all the way is just a molten version or a quantum disordered version of the pi Néel state. So that's spectacular, fine, good. Then we also measured the fidelity, because okay, you could have a phase transition which doesn't break any symmetry. You could have a 0 temperature phase transition. So then the better thing is to look at the overlap of the wave function at a certain point in parameter space. So here, the black arrow that is drawn here, we have taken that straight line within the river of liquidity here and computed the fidelity as we move along this line. And you see that 1 minus psi of lambda, lambda is some point here, with lambda plus delta, one remains 0.998. So the overlap with the excited states is not happening. I mean, most of the weight is in the same ground state, and that the fidelity is not showing any anomalous behavior all the way till here. You see the number reaches only 10 to the power minus 3 as we go from this point till that point. So this is the evidence from fidelity on 32 site clusters that it's highly unlikely that there is any kind of a phase transition along this line. Good. Then you can do the other axis, which is go from the checkerboard lattice, go from the Shastry-Sutherland lattice to the checkerboard lattice by adding the missing diagonals in these things, which is this axis of the triangle. And again, we find a river of liquidity here, which is connecting. This point here is the Shastry-Sutherland, and you add the other diagonals, the green ones here, which is the checkerboard. When the green equals the pink, that's the diagonal. And if you go the other line, it's back to the Shastry-Sutherland, so the phase diagram is symmetric about this diagonal. And now look at this. This is the level spectroscopy as we go along the vertical axis till here of all the low-lying levels within the different irreps. It's totally featureless. Nothing happens as you go from the Shastry-Sutherland to the checkerboard. There is a river and nothing, and there's no phase transition, it seems, between the two. The third thing is you can go from the checkerboard back to the J1, J2 by adding all the empty squares which were there, by filling them up by, say, these ping bonds, right? Again, we find the same river of liquidity connecting the two, where there is no Néel order and no VBS order. And again, if you look at the low-lying levels, there are no level crossings. There's no real along the river, along the yellow points. This is along the yellow points chosen in the middle here. So the thing is, it seems now that we have a large rivers of liquidity, and if you connect the three, it forms a triangle of liquidity between these three models. And this brings me to the next question. What could be a wave function which interpolates between these three models? For a particular system size. N is equal to 20, and we also have 32 site data. The river becomes broader. The change in the width is in the third decimal place of the coupling.
In other words, this river is not like a phase transition.
No.
But it's a phase.
It's a phase. It's a phase. Yeah. Yeah, N is to 20 also shows 0.9, yeah, 0025, even higher. But the thing is that we cannot do scaling with fidelity susceptibility because we have very limited system sizes. So, and if I was able to do quantum Monte Carlo, I would have done a full data collapse of the fidelity susceptibility. So to the degree we have up to 32 sites, yeah. Ooh. Oh, sorry. Yeah, for the robustness, sorry. Yeah. Yeah, there's no change in the low line. if you throw randomness. If you start pulling out the thing, then there'll be, because the picture I'm going to present is that of a Dirac spin liquid that will induce a residual density of states that'll basically cause a finite thermodynamic signatures in terms of kappa over T, and thermal conductivity, there'll be residual if you extrapolate to zero temperature and things of that sort. But you mean vacancies, right? Yeah.
Instead of other particle is which of all of them.
Oh, those extra bonds, if you just throw in some of them. That's a good question. I should look into that. I don't have a right away answer. Yeah. I just adiabatically try to turn off the couplings and turn on and interpolate, but that's a good point. I have to look into that. Right. Okay. So the model that I'm going to use is that of a Dirac spin liquid, where it's pretty simple. You have uniform hoppings on the lattice coupled by D-wave pairing. And there is evidence from variational Monte Carlo on the square lattice that is in 2013, then followed by more unconstrained Monte Carlo from the Japanese group, providing evidence that this is a D-wave gapless Z2 Dirac spin liquid with a certain weird name that appears in Xiaogang Wen's classification. Okay, then came the evidence about 3 years ago from various approaches, from level spectroscopy of ED, from these two papers by Anders Sandviks and company, from FRG, from these high-end IPEPS calculations, from neural networks, that the phase diagram on the Shastry-Sutherland looks like this, that there is antiferromagnetic order plaquette and some spin liquid in between. But again, the nature of the spin liquid remained at large. There's also alternative pictures that it's not a phase, but there could be emergent symmetry, O4 symmetry, that rotates between these order parameters, and there could be a deconfined quantum critical point. What I argue is that this thing is proximate in parameter space from which the spin liquid descends, and that's why it's gapless here. And so there are, of course, different views that it's not a phase, but just a point, sort of, a critical point. Then there is this evidence based on these presidymium compounds, which looked at the behavior of the specific heat and observed a T-square dependence over a certain temperature range. And they also measured kappa over T. And in zero field, you see that the kappa over T extrapolates to a finite value, just what Yogesh was saying. If you have a picture of Dirac nodes, but for this finite kappa over T, you need a Fermi surface. So what's mostly happening is that the spin-ons are experiencing a random potential due to disorder, and that is inducing a finite residual density of states, which leads to this finite kappa naught over T in this regime. If you look at neutron scattering, it's featureless. It's like what you saw in Kagome compounds, that there are no sharp Bragg peaks, there are no particular. And then if you go down in energy, down to the elastic line, there's a continuous increase in the intensity, but no sharp magnonic features appear in neutron scattering. So they have again argued, principally because of T-square, that it could be a Dirac spin liquid behavior. This is the kappa naught over T observed in various other systems, and the one in this compound is among the largest that has so far been observed in magnetic oxides. Good. So now you come to the fact that, okay, you believe it's a Dirac spin liquid. That's what is known from the square lattice. Can you systematically enumerate spin liquids on the Shastry-Sutherland checkerboard and try to see if indeed a Dirac spin liquid would interpolate between all three lattices and could explain the observed features? So the way to classify spin liquids is to rewrite the spin operators in terms of some fictitious quasi-particles, which are spin 1/2 and charge neutral, called spin-ons. This allows you to have extra symmetries in your problem, namely SU2 gauge symmetry. That is what you can do to the fermions to keep the spin operator invariant, but leads to the appearance of unphysical states, that is empty and doubly occupied, which have spin 0. They can be projected out. But the most beautiful thing of this parton representations is that you have particle hole symmetry, which doesn't commute with the phase rotation, leading to an appearance of an SU2 gauge symmetry. And all you need to do is to find projective realisations of lattice symmetries up to SU2, U1, Z2, or different subgroups to identify spin liquids. So that basically, in another language, boils down to classifying quadratic tight binding spin-on Hamiltonians. What are the allowed hoppings and the pairings, and what are their phases? And it turns out that the simplest state that you can define, which is like the mother or the parent of all states, is a simple tight binding Hamiltonian with a pi flux threading through the square lattice, which leads to this picture of 4 Dirac cones at pi half, pi half. If you Gutzwiller project this state beyond mean field, it already leads to excellent energies on various lattices, and many of them have been claimed as excellent variational descriptions of this. And this also serves as a state which allows you to study transitions into Néel order and VBS order, and that has sort of been described as in this paper on unifying description of competing orders by treating such simple pi flux states on various lattices as the parent states. Okay, so we did this classification. It lands up, you land up with about 60 odd spin liquids with U1 gauge groups, basically telling you what are the different patterns of the flux that the spin-ons experience as they hop on a lattice. And you can then add pairing instabilities to lower the gauge group to Z2, and then you can sort of classify these Z2 spin liquids and identify another bunch of 80 of them or something. And then I say there are 2 solutions to the problem. Either you sacrifice a PhD student for 3 years who goes through 144 states and then starts finding which is the best one, or you use some clever ideas. And the idea is already that this state should be connected to the square lattice state. And we know what the square lattice state is. So Xiaogang Wen classified square lattice states, and he found 272 of them. One of them is what I told you, this particular D wave. And what you can do is so my postdoc then looked at Xiaogang's state and found what is the equivalent one in our classification. Fine, defined by some hoppings and pairings. And then you can do study of energetics by going beyond mean field and enforcing this constraint of 1 fermion per site exactly by killing these doubly occupied and empty sites, which is possible to do exactly in Monte Carlo because it just implies calculation of Slater determinants, which can be done in polynomial time. This is also the reason why we use fermions and not bosons, because bosons would need permanence, and nobody has come up with an algorithm which can compute permanence in polynomial time. That's a practical view. What this means, the projected wave function, if you want pictorially, as Kedar said, you just have non-overlapping dimers. You have an RVB picture, and from every site is only part of one singlet, and then you have this massive superposition so as to restore symmetry, but you basically kill configurations like these, which are unphysical, where you have a site being part of 2 dimers. This is what projection means in that language. From this, you can compute energetics and everything, and now I'm going to really come into a bit of detail why, sorry? Yeah. So in this scale, I have, like in the square lattice, there are 2 free parameters. I have 4 here, the Shastry. So this is the beauty of the variational approach as opposed to brute force methods. For example, the Laughlin wave function has no variational parameter. I think that's the most beautiful part of it, right? Here I have 4, and I'm going to show you with 4, I beat energies which are done with 1 million parameters, okay? So if you have, so this is a simple wave function. I have just hoppings, S wave, and D wave pairing, period. If you look at where the position of the Dirac cones is, on the square lattice, it is possible to define a gauge where the Dirac cones are precisely at pi half and pi half. The moment you're away from the square lattice, we show that it is impossible to define any gauge or any wave pairing which preserves the Dirac cones at pi half, telling you that the spin excitation in the dynamical structure factor will not be at pi. Will not be. This indeed is the case we showed here. That happens simply if you just calculate the channels of scattering. So you have a Dirac cone at pi half, which splits into 4 Dirac cones, I show here. And you start calculating the inter-Dirac spin-on scattering. And you see that the principal weight will occur at pi plus minus 2 epsilon. Okay, this is what you would expect. I'll show you from an independent Keldysh FRG approach, which knows nothing about symmetries, nothing about this wave function. This is where you get it, okay? Okay, so once you predict a wave function, its quality is typically like of this, water, okay? Okay, not that bad quality, I mean slightly better we have. And the goal of improving, unless you have the Laughlin state, okay, which is much better quality, my quality is something like this. You can improve the quality of the wave function by a technique called Lanshaw's. Lancers means applying powers of the Hamiltonian. And unless your wave function, the starting one, is totally orthogonal to the ground state, you will, after sufficient number of steps, converge to a true ground state. And you will reach a water of this quality, which we need. So we know from quantum mechanics that if you have an exact eigenstate, like the ground state, the variance of that is 0. So what you do is, the quality of a wave function is not just measured by its energy. I can always cook up wave functions which have excellent energy, but have nothing to do with the ground state, simply because their variance is very large. So energy and the variance have to be looked at together. So a typical thing would go like this. You start from a random state, okay? And then you do Lancers. And you see you converge in some non-monotonic way to the true ground state, okay? The power of the PSG approach is that you don't have to start from somewhere here, where the convergence is non-monotonic, but start from somewhere here, such that if you do even a couple of Lancers steps and extrapolate to 0 variance, you will reach the true energy. This is, for example, shown here. You start from a wave function, a Z2 spin liquid, you do 1 Lancers, 2 Lancers, and you extrapolate, and actually you reach the Lancers energy. So the beauty is to start from a reasonably good trial state. Indeed, this is what happens for our Z2 Dirac spin liquid. You take various cluster sizes, L equal 10, 12, 14, you keep on. And then you converge here. This is with my wave function, and this is a wave function from neural networks, which has about 1 million parameters or so. You see that the accuracy. So if you get the physics right, you don't need an unconstrained optimization of the wave function. And indeed, if you do extrapolation to the thermodynamic limit from my approach here, VMC wave function with 4 parameters, or you do from DMRG, you converge to a value which is equal within error bars in the thermodynamic limit, telling you that the wave function is energetically competitive. Good. Energetics is one thing. Sorry? But DMRG will, of course, because of cylinders, will converge from above. And if you do tori, you will converge from below. Yeah. So if you now, okay, that's one thing. The second thing is, what about spin-spin correlations, real space? So this is data from Anders Sandvik's paper, which computed the power of the decay of the spin-spin correlation, which can be extracted from how the magnetization falls in with the system size. So at 0.8, which is the middle of the spin liquid, they computed that the power is 1.3 roughly. That's how the spin-spin correlations decay with this thing. This is my results from VMC, and this is from Federico Becca and company using transformer neural network wave functions. And if we fit to the critical form, r to the power minus z, we get 1.3 with an error bar of 3. So telling you that we agree with DMRG and unconstrained neural networks, and that the wave function that I've proposed to you, which is highly constrained by symmetries, is essentially giving you the same power law decay as obtained from unconstrained methods. And if you go along this river of liquidity, you actually then reevaluate these exponents, you merge to the square lattice, which is around 2. So it continuously evolves. This is another signal that it's a Z2 Dirac spin liquid. If it was a...
Phase has continuously varying.
Yes, if it's a U1 spin liquid, it's not a continuously varying. That has a universal power law. When the exponent evolves, it's actually a Z2. That's an indication of a Z2 spin liquid, not a U1. It's a known fact. It was established first by Hermele and others in late 2000s, 2008, 9. There's a paper which shows this, that because of this, yeah. So we sort of, yeah. And then you can compute the spin-spin and the dimer-dimer. You see that they evolve with, this is also what has been observed on the square lattice, J1, J2. On the Kagome, this won't happen. On the Kagome, you will always get a power of 4 because that's a U1 Dirac spin liquid. Indeed, what we did was to compute the spin-spin correlations in real space equal time, starting from one site to all the other sites on a 36-site cluster, and you see the agreement. This is the exact result, empty circles. This is my Z2 spin liquid with 2 Lancers steps, and I get the sign of all 35 correlators correct, and look at the magnitudes also, all in place. Not one correlator is off. And then somebody criticized, well, this is 36, can you do larger? Well, in larger, you can't do ED, but you can do neural networks. So I asked Federico Becca for data on 196 sites, and this is the agreement with my Z2 Dirac spin liquid, and this is the blue squares are neural networks, and all 195 correlators agree in sign and in magnitude, telling you that the wave function with 1 million parameters is essentially being reproduced by a wave function with 4 parameters. Because you have basically got the symmetry correct. Yeah, sure, I'll wind it up. Sorry? Dip, oh, that's just the sign of the, no, I'm plotting what? The absolute value of the spins, no, this is the sign. Antiferromagnetic, ferromagnetic, antiferro. They're just oscillating in sign as it's going from side. So you go from one like a snake-like path, and you compute S naught with Si. And as you go along the sides, I'm just comparing. Okay, coming to the broader picture. Then you take and you compute the equal time spin-spin correlator. That's for the Z2 Dirac. This is from the neural network, Federico and Sebastian and Luciano and company. You get peaks at pi pi. But now you will disagree with me. Well, I told you that there's a splitting of the Dirac cones into plus minus epsilon. So how do you get the peak at pi pi? This is because I'm simply integrating the structure factor to get equal time over frequency. This is the result from the Keldysh FRG, a method purely based on correlators which knows nothing about wave functions, nothing about symmetries, brute force RG. You see that there is the dominant spectral weight is not at pi pi. Okay? So this is FRG done on the real frequency axis. Sorry, question? Okay. So now from the picture of this Dirac spin-on scattering, you will see that there is, okay, let me show you here. Right. So this is the dynamical structure factor obtained from Keldysh, the one below. This is the mean field result here. I've plotted it along the path gamma to x, which is pi 0, fine. Then as you go from x to m, this line here, you see that this is where one of the dominant weights occurs. And then as you go from m to gamma, the other weight occurs. This is precisely what would happen if the Dirac cones have shifted. They're no longer at pi half, pi half. So then the spin excitation cannot be reconstructed at pi pi. The spin excitation has to be away from it. This is evidence that basically this is happening from this picture of Dirac cones which have split into 4. And the subdominant intensity is at pi pi. In fact, if you plot the structure factor at omega equals to 0, you see the split here. But when you integrate over omega, sorry, omega integrated, not omega equals 0, omega integrated, then the peaks are recovered at pi pi, because this is pi pi, there are high energy branches here which add to the spectral weight and wash out the splitting. So this is not seen in the equal time, but this is seen in the low frequency structure factor, the static one, not the equal time. So this is independent evidence of the picture of Dirac spin-ons being away from pi half that I was telling you. Now, if you go from the square lattice, if you go from the Shastry-Sutherland to the checkerboard has a larger symmetry. Some mirrors are restored, and you can again define an ansatz in which the Dirac cones occur at pi half, and then we see that the spectral weight shifts back to pi pi. So the prediction from projective symmetry groups and wave functions is exactly going one-on-one with the predictions from an independent approach here.